Okay, the first derivative test. Not a real test, but it's a test you use to see what's happening on the curve, right? So Fermat's theorem states that if f has a local max or a local min at c, then c is a critical number, which means that the derivative is equal to, what would fit in the small blank? 0, or it does not exist, right? So we need to find the first derivative, right? And then we're going to use it in this first derivative test. And we need to find where it is 0 and where it does not exist. But not every critical number gives a local maximum or a local minimum, right? There might be other stuff happening. When we determine the critical numbers, how do we know if there is a local max or a local min or neither, right? And we've already hinted at this enough that you should have a pretty good idea. But locate the critical numbers on the function shown to the right. State the sign of the derivative for each interval defined by the critical number. Okay, so I'm going to trace along and you're going to say critical number. Critical number. Okay, I'm going to trace along, critical number. Trace along, and you say critical number. And then down to here. So that's where the critical numbers are, right? So where are they? They are where the derivative is 0, which means that we're turning or we're flattening out, right? So the derivative there will be 0, or it does not exist, right? You got a corner. Okay, so on this interval, what's the sign of the derivative? Okay, so that's negative. On this interval, positive. On this interval, negative. On this interval, and on this interval. Okay, so what happens when we go from a negative to a positive? And what do we have going on there? We have a minimum, right? You see me doing it, I got hands go right in front of me, go, okay, you got negative to positive, minimum. What happens when you go from a positive to a negative? Your maximum. What happens when you go from a negative to a negative? And the mark is a minimum. It's not a max or a min, right? There's something going on here. There's a name for this. Anybody know the name? You know the name. It's the point of inflection, but we aren't getting there yet. And then you go from negative to positive, and you have a minimum, right? Okay, so the first derivative test. If c is a critical number of a continuous function f, if f prime at x changes from positive to negative at c, then it has a local maximum, right? At c. If f of x changes from negative to positive, then it has a local minimum at c. If f of x does not blank at c, then f does not have a local maximum or a local minimum at c. So if it does not change signs, right? It doesn't change signs. You see that sign change stuff sometimes on those devices you no longer use, known as calculators. And when you're trying to figure out a 0 of a function on the calculator and you hit 2 points that are above or something, it'll say error, no sign change, right? So it's looking for that. Same thing. If you actually try and do a max or min on the calculator and you don't go either side of it, it'll say error, no sign change. What's it looking at? It's looking for the derivative. It's looking for where the tangent is 0, right? And it says, that's where the max is. Doesn't really say, that's where the max is. Determine the local max and min values of h of x equals x to the 4th plus 2x cubed minus 2x plus 5, and sketch the graph. Okay, so what do we have to do? Well, we got to find the derivative, right? So we need h prime of x. This is about as simple as a derivative as you could ever be asked to do, right? Okay, so I'm not going to insult you by asking you for it. I'm just going to write it out. Okay. All right, and then what do we need to find? Well, we need to find either where that is 0 or where it does not exist. It doesn't not exist, right? I mean, it exists everywhere. It's just a cubic, right? So that exists everywhere. What would make it not exist? We need a denominator or we need a radical, right? And that point, then there's place, okay, hey, you can't divide by 0 and blah, blah, blah. Okay, so what do we want? So that's equal to, well, let's factor out a 2. So we are going to need to, wait a sec. Oh yeah, that's right. We are going to need to find a 0 for that, right? So 1 won't do because that'd be like 2 plus 3, but negative 1 might have some, so it'll be like negative 2 plus 3 minus 1. So negative 1 is going to be a 0, right? It's like back to, when do you guys do this now? It's like 30-1, I guess. Used to be 20. Yeah, you do all that rational 0 stuff, and yeah, I haven't taught 30-1. I don't know. So then we got a factor of x plus 1, and we've got 2x cubed and 3x squared and no x's, and a minus 1. And 1 times 2 is 2, and 3 minus 2 is 1, and 1 times 1 is 1, and 0 minus 1 is negative 1, and 0, right? That's got to be a 0, or you got it wrong. Okay, right? Remember that stuff. So, since since negative 1 was the root, then x plus 1 is the factor, and the other factor is 2x squared plus x minus 1. So that, hopefully, factors. What do I need, a plus and a minus? 2x squared. By the way, when you factor, FOIL it out. Honestly, seriously, what does it take? 5 seconds? Not even? Because some of you are losing marks because you're getting signs wrong on something because you just factored it wrong, right? No, you got it. Just quick check, right? 2x squared plus 2 minus 1 is plus 1 minus 1, right? Generally, the mistake isn't in I couldn't find two numbers that multiplied to 1. The mistake is I got my signs wrong, and that if I really FOIL it out, I get a minus 1 there, and then it all goes to heck, right? Because now your roots are wrong. And, making mistakes not necessarily bad, but when the mistake leads you to really ugly answer, like, hey, if you'd have just put a 1 in there, which is a number you're supposed to put in there, it was very simple to work out. When you put that root 17 in there, because now you had to use the quadratic formula because you had the sign wrong, and so now it doesn't factor, right? At some point, you need to kind of say, would they really do this to us? The answer is always yes, of course, but are they going to at this point? Like, really? Do I have to use the quadratic formula for this? I always kind of pause at that moment and say, I might have messed something up here. Like, maybe this just does solve kind of easily. Let me just go back and look at this and then say, yeah, they really do want me to. At which point I would leave it, go on, and come back to it later. Okay, because it's just too much time, right, to do. Anyways, we got this. So what have we got? Well, we've got 2x plus 1 squared and 2x minus 1. So h prime of x always exists, right? And is 0 when x is negative 1 or positive 1/2. Okay, so. Always exists. Right, because critical numbers are where it does not exist, so there are no, or where h prime of x equals 0. So h prime of x equals 0 means that x is equal to negative 1 or positive 1/2. And now, we want to see what's going on the intervals, right? So, like, what's happening and what are we splitting this up into? And I'm going to flip it on its side. So we've done some examples of this where on the chart, I'm going to do the chart the other way, and you can just kind of see which one you like, right? And you might say, I like the way that you did it, which is the way the book does it, or you might say, hey, I kind of like this way that we're looking at it now. And that is, what I'm going to do is I'm going to draw a number line, okay? And I'm going to put the critical numbers on the number line. relative positions, right? I'm not going to put the half here and the -1 over there. So there's a -1 and there's a half, right? So we're splitting into 3 intervals, right? And we've got okay, let's do this. So we've got the 2, we've got the x plus 1 squared, and we've got the 2x minus 1. Okay, so the 2, good. I really messed up. Okay, never mind. I gotta redraw this. I need more space. All right, hang on. Okay, wait, I can fix this. Okay, there. I need some room there. I need this. Okay, I need more space. Hang on. I'm just going to go to the end here. Okay, hang on. So sorry. Okay, so we got the 2. We got the x plus 1 squared. And we've got the 2x minus 1. Okay, so the 2 is always positive, right? It's just 2. Okay, because then down here we've got h prime of x, and then here we've got h of x. So x plus 1 squared, that's always positive, right? It doesn't matter what you put in there, you're going to square it, so that's always positive. The 2x minus 1, okay? So if we have, like -1,000,000, or that's going to be negative in this interval. Throw a 0 in there, it's still going to be negative in this interval. And then above a half, whatever, it's going to be positive. Okay, so then what's the derivative going to be? Well, we've got a positive times a positive times a negative. The derivative will be negative. That tells us that it is decreasing in that interval, going down to the right. We have a positive times a negative, which is a negative. That tells us that it's decreasing in this interval. And we got a positive times a positive times a positive, which is positive. And that tells us that it's increasing in this interval. So doing it this way, we can kind of see, hey, you're going to have a minimum here, right? Because you're decreasing, increasing. Right? Where is that? It's at a half. So looking at this chart, we can see that we've got a local minimum when x is equal to 1/2. And so we need to figure, well, so what's that point, right? So what's h at 1/2, right? So we go back to the top definition, right? So it's 1/2 to the 4th. Plus 2 times 1/2 cubed. Minus 2 times a half. Plus 5. Okay, so then we work this out. So 1/2 to the 4th is 1/16. That's 1/8 times 2, so it'll be like 1/4. That's 1. And then that's plus 5. So we need 16ths, right? Common denominator. So we got 1/16 plus 1/4 is 4/16. This is plus 4, which will be 64/16. Okay, so I've done two things, right? I've combined these two guys to get plus 4 and then changed it to over 16. And we're going to get 69/16. And if it reduces, you should reduce it, right? Okay, so always reduce. It's one thing a lot of people missed. It wouldn't affect your final answer, but it would affect your process. Was we had one question where the first derivative was like 12x squared over 3y squared. If you make that 4x squared over y squared, it's going to make the next step, quotient to that a lot easier, right? Because you're not going to have to deal with bigger numbers. Okay. So if you look at, if you work something out and you say, hey, wait, this cancels down, do it at that point, right? It just makes it easier when you continue on. Okay, so we have a local min at 1/2, comma, 69 over 16. What else is going on? Well, something's happening at -1, right? And we're getting, it's going to flatten out. The curve flattens there, but it's always so it's decreasing to 0 and then decreasing. That's that inflection point. That occurs at -1. So here, so at -1, so h of -1, right? Also a critical point, is -1 to the 4th plus 2 times -1 cubed minus 2 times -1 plus 5. So that's 1 minus 2 plus 2 plus 5, which is 6. Okay, actually I can move that down, right? So we've got something happening at 1/6. Sorry, -1/6, right? So we've got -1/6. And what's happening there? So. Okay, so we got the point -1/6 here. Oh, wait, let's move that in a little closer. And we've got the 1/2 and 60, that's like 4 and 5/16, so like, that'll be about like here. Okay, so what's happening? Well, it's decreasing to here. Decreasing, 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 flattens, decreasing, and hits a local minimum, which means you can't drop down there below that. So it flattens out, decreases to here, and then increases. Okay, so that's kind of what our curve is going to look like. And for a better shot of that, then there it is there, right? So we've got, oh, it doesn't want to show stuff. Okay, we got here, minimum, yeah, it's not going to show the inflection point, but we've got our, there's the 1/2 and 69 over 16. Okay, so that's that. First derivative text. Go back. Right. Determine the critical numbers, the intervals of increase and decrease, and local max and min values. Okay, so we're not asked to sketch this. We will be getting into that more after the break, right? Because the title of this thing is Extreme Values and Curve Sketching, right? So we will get a lot more into the curve sketching. We do basic polynomial right now. Critical numbers, intervals of increase, decrease, and local max and min values. So we got to find the first derivative. When you use the product rule, if you do it backwards, it mildly disturbs me. You're not going to get it wrong. It's not what I want to see, right? Because I'm looking for, 3x squared times that plus the other way. If you do the quotient rule backwards, then it's wrong. Okay, it's just wrong. So, if you try and maintain the correct order, it's going to help you out, right? So it's 3x squared times, well, okay, wait a sec. Let's do this first. Let's do this first. So g of x is 3x squared times x plus 1 to the half. Okay, so let's do that first, right? Okay. Now, we can do the first derivative. So g prime of x is 3x squared times 1/2 x plus 1 to the negative a half times 1, right? Really? Because I have to take, but, let's write it out. Times 1. Okay? Just so we know, hey, yeah, you really did find the derivative of the inside, which is just a 1, right? Plus. So it's all there, right? If you always do it all the time, you're not going to forget to do it when you need to do it, right? And that's all of a sudden, oh, there's no, because this was an x squared, and then that's going to be a 2x, and then all of a sudden it's not there, right? So, show it. Times the derivative of 3x squared, so that's 6x, and the original expression, right? So the x plus 1 to the half. Okay, so now what do? Well, we factor out what we can factor out. So, well, or let's clean it up first, right? Let's clean it up. So 3x squared. All right, so good idea to clean it up first, right? Let's just combine that first. You know, don't do too much at once. I think that's the big rule here, right? Don't do too much at once, because then you start making mistakes, right? It's very easy to make mistakes if you try and do too much at once. Okay, so let's get that 3/2 out of there. And let's get an x out of there. And let's get an x plus 1 to the negative 1/2 out of there. Okay, so that's going to be my common factor, right? So that leaves me with, in this term, I've got everything except that's just an x, so there'll be an x here. Plus, so I need 3/2 times something gives me 6. Now I can just take the 6 and multiply it by 2/3, right, and get 12 over 3, which is 4, right? Because 3/2 of 4 is what's going to give you 6, right? So just make sure whatever you put here, when I multiply this times this, I get 6. The way you do it, you take 6 and divide it, multiply it by 2/3, right? Multiply by the reciprocal. That'll give you the number you need to go here. So you got the 4, and then the x plus 1, right? Okay, and now we're just going to simplify this here. So we got 3/2 x. Actually, you know what? Let's put stuff where it belongs. So up top we got a 3 and we got an x. This goes on the bottom, right? And it goes on the bottom under a radical. So along with the 2, right? The 2 goes on the bottom. So the 2 belongs on the bottom. This belongs on the bottom under a root sign because it's minus a half. We get the 3 and the x, and then up here we got 5x plus 1, right? So in brackets, 5x plus 1. Plus 4. 5x plus 4, just what I said. You know what? Yeah, don't worry about it. Just push it in, push it out of the way a bit. 5x plus 4, just goes right there. Okay, so we're in a fully factored form here, right? Which is what we want, because now you could say, hey, if x is 0, you're going to get 0. If x is negative 4/5, you're going to get 0. If x is negative 1, you got a problem. As a matter of fact, x can't be negative 1 or below, because then this thing is just totally undefined, right? So x has to be greater than negative 1. So negative 1 is a critical number, right? It doesn't exist there. And then we've got 0, and we've got negative 4/5. Okay, so critical numbers. So g, is this g? Yeah, g prime of x does not exist when x equals negative 1. Okay, got a problem at negative 1. And g prime of x equals 0 when x is 0 or negative 4/5. Okay, 0 or negative 4/5. So we need to go and find those intervals, right? So I'm going to go to a new page now. Another new page. I'm going to do a little number line, right? So I've got negative 1, but not including negative 1, right? And I've got negative 4/5, and I've got 0, and then it continues on that way. Okay? And I've got let's put a line there. And so the factors we've got are a 3x. We get the 5x plus 4. We've got the 2. We've got the root x minus 1, which is going to give us our sine of g prime of x. And then it's going to tell us what's happening on g of x, right? Yeah. Root x plus 1, right? At least that can be fixed without erasing. Okay, so in this interval will be negative, right? 3x, x is going to be negative. In this interval, 5x plus 4, well, 5x plus 4 will be like, so what's it going to be in here? So now you either put a number in there that's between negative 4/5 and negative, it's negative, right? Yeah. So what you can do is say, this is negative 4/5, this is negative 5/5. Find a number between them. So then go to tenths. Negative 8/10 is negative 10. You go negative 9/10 if you want it, and you put that in there, and you got negative, it's negative. Okay? You got to figure that out. Yes?
If you do it the chart way, do you not put in x is less than -1? So it doesn't exist.
Right. X is doesn't exist when it's less than -1.
Okay.
So, yeah. Yeah. You don't need to worry about less than -1, right? Because there is nothing there. 2 is always positive, so we can just go fill in for the 2's. And the root of x plus 1, square roots are always positive, right? So remember, that's what this symbol means, right? The radical sign is the positive or principal square root. So those have to be positive numbers. Okay, so g prime of x is positive, right? Plus, plus, minus, minus. This is positive. This is increasing on this interval or going up. Remember to always draw to the right because we're going from left to right. We never did here. So if you're between 0 and negative 4/5, you're going to be negative here. And if you're above 0, you're going to be positive. And then between 0 and 4/5, this will be positive and this will be positive. Okay, so now we're filled in. So we have a negative times positive times positive times positive, which will be a negative in this interval. So it's decreasing, giving us a local maximum at negative 4/5. Okay, you can see that, going from increasing to decreasing. And then here we've got positive, which is increasing, giving us a local minimum at 0. So we have a local max at negative 4/5, and we have a local min. Okay, so you can write that in here, right? This is a local max. This is a local min. All right, so let's figure out what's happening. Or sorry, let's figure out what those points are, right? Because the original question said, determine the critical numbers and the local max and minimum values. Okay, so we have a local max at negative 4/5. Going to, where should we do this? Let's clean this up a bit. Okay, so local max. So we need g at negative 4/5, which is equal to 3 times negative 4/5 squared times the root of negative 4/5 plus 1. Okay, so that's 3 times 16 over 25, right? This will always be positive, so. And then negative 4/5 plus 1 is 1/5. And so we've got the root of 1/5. And so what do we got? We got 48 over 25 root 5 times root 5 over root 5. So the root of 1 over, 1 over the root 1 is just 1, right? So we got that root 5. We'll rationalize the denominator, giving us 48 root 5 over 125. Okay, so we have a local max at negative 4/5 and 48 root 5 over 125, right? So, and those are exact values too, right? Well, especially negative 4. No, I mean, they're both exact values. And we have a local min at 0, right? right? Local min at 0. Let's say when x equals 0. So g of 0 is 3 times 0 squared times the root of 0 plus 1, which is 0. So you have a local min at 0, 0. Okay. Now, if we wanted to list intervals, right, like where it's increasing, decreasing, so we'd say g of x is increasing on the interval, so it's from -1, but not including -1, right? So open parenthesis -1. We're not including -1. You can't put a -1 in there. So from -1 to -4/5. It's also increasing from 0 to infinity. Have you guys used this before? Is it union? Yeah? Okay, good. I know we do that in 30-2. I don't know if you do that. Do you do that in 30-1? Yeah? Okay, good. And it's decreasing just in this interval, right, which is -4/5 to 0. And you're always looking at round parentheses, right, because it's at -4/5. The critical number is this number, right, because it's not included in the interval, right? It's not part of the increase or the decrease where it hits 0, right, or does not exist. And then same thing here, right, these guys. Okay, and that, and so if you want to look at that, I can turn this one off and turn that one on. And so, you know, there it is there. There's -4/5, right? And then that's whatever, 48√5. If you worked it out, 48√5 over 125. And there's your local min at 0, 0. It didn't say sketch, but I just thought, you know, why not, right? Okay. Back one more. Determine the absolute minimum value of f of x is equal to x plus 1 over root x. So the absolute minimum value, that can occur on a boundary if there's anywhere that you know, it's oh, well, it says x has to be greater than 0. So it could be at 0. That's a boundary, right? Well, or really close to 0. It can't be at 0, right? Or somewhere else. So absolute maximum value of. Okay, so f of x. So you might want to rewrite, just say f of x is x plus x to the -1, right? Can help you in finding the derivative. It's sort of specified. So f prime of x is going to be 1 minus 1, how do we want to do this? Minus x to the -2, right? I'm okay if you just want to go straight to -1 over x squared, right? That's your choice. You get it wrong, there's a problem, but if you don't. Now we want to combine this. Okay, so we might want to write it as x squared minus 1 over x squared. Okay, it's going to make it a little bit easier to evaluate, right? Like where are the zeros? So when x squared minus 1 is equal to 0, you're going to have a 0, right? Which could be a max or min. Which means that x is plus or minus 1, but we're only worried about this interval, right? Okay, so what are we going to do here? So we want x squared minus 1 over x squared is equal to 0, which means x squared minus 1 is equal to 0, and x squared is 1, and x is plus or minus 1. Okay, but we want x greater than 0, so x equals 1. Okay, that's all we're going to look at, is just x equals 1. So now we're going to look in the intervals, right? So not including 0, between 0 and 1, and from 1 up. So here's the number line. This is 0. This is 1. Draw some lines down here. Okay, we got factor. Oh, wait, this is really like x plus 1, x minus 1. Okay, so we have three factors, right? We got to look at x plus 1, we got to look at x minus 1, we got to look at x squared. So x plus 1, x minus 1, and x squared. Okay, well, x squared is always positive. It doesn't matter what and the numbers here are actually always positive anyway. So x squared is always positive. X plus 1, since we're going above 0, right, it's just going to be positive. But x minus 1, when you've got like a half in there, this will be negative here, and then it'll be positive. Okay, scooch down a smidge. So we got two more things to put in here, right, which is, what was this, f of x? So f prime of x and f of x. Okay, so f prime of x will be negative. This is decreasing. And f prime of x will be positive. This is increasing. Okay, which means this is a minimum. It's a local minimum, right? Local min. Question is that also the absolute min, right? So when x equals 1, f of 1 is 1 plus 1 over 1, which is 2. So we have a local min. Now it also has to be the absolute min, right? Because as we're coming from here, we're going down, we're hitting here, and then it's up. So that is the local and the absolute minimum, right? So local and absolute minimum at 1, 2. Okay, wait, let you finish that. I go too fast, right, Katie? Yeah. Words from the hall. Yeah, you do. So the first derivative test for absolute value, absolute extreme values, you find the critical numbers, right? If f, so this is for the absolute. If f prime of x is positive for all x less than c, and f prime of x, so it's positive for all x over there, right? Positive. And f prime of x is negative for all x is greater than c, going that way, then f of c is the absolute maximum. If f prime of x is negative for all x less than c, right, over there, and it's positive for all x greater than c, then we have the absolute minimum. Okay. E was way too big. Even and odd functions. Okay, so we've got to do at least 2 today, so we'll have to do this one too. Describe the symmetry in each of the following functions. So how is this function symmetrical? Or this? Or this? Reflection in the y-axis, right? Okay, so it's a reflection in the y-axis. So it's symmetrical about the y-axis. Yeah. Okay, now we've got the three functions, right? F of x equals x squared, f of x equals 3 cos x, and f of x equals the absolute value of x. Functions with this kind of symmetry are said to be even functions. In other words, even functions are functions that are symmetrical about the y-axis, right? I mean, we're just basically repeating what we already wrote. So it's an even function if it's symmetrical about, or a reflection in, right? So you guys did all this reflection stuff. It's a reflection in the y-axis. If you examine the graphs above and compare the value of each function at x equals 1 here, and -1, or 1 and -1, or 1 and -1, then what can you say about those values? They're the same, right? So if f of 1 is equal to k, then what's f of -1? So we're saying this is k, then what's this? Okay, this is k, what's this? K. This is k, what's this? K. So if f of 1 equals k, then f of -1, or in general, if f of x is some value k, then f of -x is that same value k. The function f of x is an even function if and only if, that's the bicondition, right? So it works both ways, right? You can read it one way, you can say if, or you can read it the other way around. So only if f of -x is equal to f of x. Right? So if we want to test, and what does this say, right? Like when you replace x with -x, the reflection in the y-axis, right? You know that from 30-1. Okay, just basic transformations. X is replaced by -x, gives me a reflection in the y-axis. And that's what an even function is, right? It's a reflection in the y-axis. Okay, show algebraically that the functions below are even by using their equations. So what I want to do is I want to do f of -x, right? So f of -x is equal to, right? So wherever I see x in the original definition, I can replace it with -x. What happens when you square -x? You get x squared. And what's x squared? That's equal to f of x. So that means that f of -x is equal to f of x. That's the other half of the biconditional, right? So if f of x equals -x, it's even. If f of -x is equal to f of x, it's even. So f of x is 3 cos x. What's f of -x? It's 3 cos -x. Now we got to do a little bit of playing with this one. So what's -x? So another way to write -x is 0 minus x. Right? And now we're doing a cosine a minus b. Right? So we look on our formula sheet and we say, what's cos a minus b? Right? Well, it's 3 times. So it's cos a cos b minus sine a sine b. Right? So that's off your formula sheet, which is equal to 3. Okay, now the cosine of 0 is 1 times cos x, right? So it's 1 times cosine of x minus the sine of 0 is 0, so that's 0 times sine x, which is equal to 3 cos x, which is f of x, right? So f of -x is ultimately equal to f of x. That's true. It's an even function. Okay? It's an even function if f of -x is equal to f of x. Right? So what you're going to do is just take the function definition, work out f of -x, and say, hey, it's f of x. It's even. F of x is equal to the absolute value. So f of -x is equal to the absolute value of -x. Now the absolute value of -x is the same as the absolute value of x, which is just f of x. That was like the easy one. Didn't have to do much there. Well, whether x is negative or positive, it's just the absolute value of the magnitude of the number. Okay? Odd functions. Describe the symmetry in the following functions. Okay, so this is a bit different. What's the symmetry here? Yeah, I kind of look at it that way too. I look at it as you're reflecting it on x and then on y, right? So I'm going to take this over to here and then down to here, right? I'm going to take this and cut there and then go down here, right? Or you could do this and then this. It doesn't matter what order you do your reflections, right? But also another way to look at it is it's a rotation. You're taking this and you're rotating it 180 degrees about 0, 0, right? So I take this and go, crank it around. Take this, crank it around, or take this and you crank it around, right? Either way, really, it doesn't matter if you rotate it to the left or to the right. If you just rotate it through 180 degrees, it's going to end up there. So we call it symmetrical about the origin. Okay, so they're symmetrical about the origin, reflecting it. I like to think of it as a reflection in the X and reflection in the Y, right? Either followed by or vice versa. Either way you like it. So it's symmetrical about the origin. And the origin is 0, 0, right? Or it's a rotation, rotate 180 degrees about the origin, or 0, 0, right? So it's an odd function. Also, it's kind of neat because this is x cubed, so that's kind of odd. Whereas x squared is kind of even, right? So any odd function, x cubed, x to the fifth, Now, on a cube root, that's kind of like, but sine x, why is that odd? Well, okay, so we'll look at that. Functions with this kind of symmetry are said to be odd functions. So in other words, odd functions are functions that are symmetrical about the origin. Examine the graphs above and compare the value of x equals 1 and x equals negative 1. So when x equals 1, we're here. At negative 1, we're here. X equals 1 and negative 1. Okay, so if f of 1 is equal to k, so this value is k, what's this value? Negative k, right? That's k, that's negative k. That's k, that's negative k. So negative k, or in general, if f of x is equal to k, then that's negative k. The function f of x is an odd function if and only if f of negative x, so f of negative x, that's kind of the reflection, right? So if I reflect it here, what has to happen to the y value? It has to be the negative of the y value, right? So if f of negative x is the negative of the original y value. Okay? So f of negative x. So I like to think of it as, if I reflect it across the y-axis, it's got to go down, right? It's got to be also reflected across the x. And that's how I look at this and say, if it's a reflection about y, then the y value has to be negative, so it has to be also reflected about x, negative f of x.
What if it was reflected only in the x-axis? Would it be odd or even?
Neither. The third case, it would be neither. Because, yeah, the symmetry is not, it would be symmetric about the x, that's not odd or even. I don't know if there's a name for that, special name. Show algebraically the functions above are odd by using their equations. So here's what we're always going to do. We are always going to do f of negative x. And we're going to say, hey, we ended up with the original function, then it's even. Or hey, we ended up with the negative of the original function, in which case it's odd. Okay? So that's what's going on. You always want to determine f of negative x. So your test, what you're going to do is you're always going to determine f of negative x. And you're going to say, if it's the same, then it's even, and if it's the negative of, then it's odd. Okay? So determine, write that, do you want to say determine f of negative x, right? So it's always the same. When you're testing for odd or even, you want to do f of negative x. Okay? If f of x, if it is f of x, so if it's the same, if you get the same value, then it's even. If you get negative f of x, so if you get the negative of that y, you get a negative y value, then it's odd. otherwise neither. Okay, so if you don't get the negative value, then it's neither. Okay, so either you get that, or you either you get f of x back out, in which case it's even, or you get the negative of the f of x, and it's odd. Okay, so what's f of negative x? Okay, that's the cube root of negative x. Well, when you're taking the cube root of a negative, you can remove the negative sign from under the cube root, right? You're just going to say, well, the cube root of a negative is negative, so it's the negative of the cube root of x, right? So if the negative's under the cube root sign, you just pull it out, right? You say a cube root of a negative is negative. And what's that? Well, that's negative, right? This is f of x. So this is negative f of x. So this is an odd function. We're going to do with sine x very similar to what we did with cos x, right? So we're going to do f of negative x, which is 3 sine negative x. So now you know what we're going to do. We're going to write negative x as 0 minus x, and then use sine a minus b, right? So that's equal to 3 sine 0 minus x, which is 3. And so that's sine a sine b, sine 0 sine x minus cos 0 cos x. Oh, sorry, that is not right. It's sine 0 cos x minus cos 0 sine x. This is why you always use your formula sheets. Right, Sid? Always use formula sheets.
Is it funny or something?
That's why you always use your formula sheets, because if you rely on your memory, you're going to mess it up, right? So
That's why you're going to.
okay, the sine of 0 is 0, so that's 0 cos x minus the cosine of 0 is 1, so that's 1 sine x. So this is negative 1 times 3, 3 times negative 1 sine x, or negative 3 sine x. Get rid of that little dot there. So it's negative 3 sine x, but sine x is f of x, right? So f of negative x is equal to the negative of f of x. That's odd. That's odd. Okay, if f of x is x cubed, right? So again, testing for even or odd. What do? You always do f of negative x. And then you say, okay, what do I end up with? Well, I get negative x cubed. Well, that's really like negative 1 cubed times x cubed, right? So negative x is negative 1 times x. This is product of a power, so you raise each part of the product to the power, so it's negative 1 times x, negative 1 cubed x cubed, which is equal to negative 1 cubed is negative 1. So this is negative x cubed, but x cubed is f of x. So f of negative x is negative f of x, and it's odd. So you got to do a bunch of these, right? Because you got to hammer it in your head which one is which. Not if I do f of negative x and get something, I got a 50-50 chance of getting it right, right? Because that's what it'll come down to, right? I don't remember which one's which. Just remember x squared is even and x cubed is odd. That is really the easiest way to figure out an odd or an even function, right? That's x squared. It's x to an even power. That's got to be an even function, so that'll tell you, right? And this is x cubed. It's about the simplest odd that you can get. So which one is which? Well, this, f of negative x is f of x, and f of negative x is the negative of f of x. So, as far as your memory, odd or even, go with x squared, x cubed.
X would be odd too.
Yeah, f of x is odd, right? Because that's just straight line, right? Yeah. So f of negative x is negative f of x, right? The negative of x, which is negative f of x. Yeah, and it's odd, right? Because it's power of 1. Those guys are easy. These guys are not so much, right? It's kind of like, well, what's this come out as? So, okay, determine whether each is even, odd, or neither. Describe the symmetry. Okay, so if you want to determine even or odd or neither, right? If you want to determine whether a function's even, you do f of negative x. So we plunk in negative x to the 5th minus negative x over 1 plus negative x quantity squared. So the negative of x, or sorry, negative x to the 5th is negative x to the 5th, right? And a negative raised to an odd power is negative. Minus negative x, so that'll be plus x. Negative x quantity squared is x squared, right? You're squaring a negative, so you get. So how does this compare to this? Factor out that negative, right? So you could write it's the negative of x to the 5th minus x over 1 plus x squared. Yeah. I know. What do I say? Well, that's odd. Okay, and that's true. That is odd. Okay, so it's symmetrical about the origin, right? Describe the symmetry. So symmetrical about origin. Okay, g of x. So what are we going to do? We're going to do g of negative x. So everywhere I see x, I'm going to replace it with negative x, right? So this becomes negative x minus 1, and this becomes negative x plus 1. Well, okay, if we factor out the negatives, so this would be the negative of x plus 1, and this is the negative of x minus 1. Okay, now I better write that. Let's put a negative 1 there and put a multiply. So it's negative 1 times x plus 1 times negative 1 times x minus 1, and negative 1 times negative 1 is positive 1. So this becomes 2 over x plus 1 times x minus 1. Well, okay, the order down here is a little different, but these guys are the same. So that's equal to g of x. So if g of negative x is equal to g of x, then we say that it's even. Okay, and that's symmetrical about the y-axis. Okay, so again, so I would do like y equals x as an odd function, or x cubed, and y equals x squared is an example of an even function, and then just remember I have to do f of negative x, and then say, okay, what does it match up with? Is it the odd one or the even one? Is it just the same y value? Do I get the same y value? Then it's even. Do I get the negative of the y value? Then it's odd. Do I get something else? Then it's neither. So if that one's odd and this one's even, this must be, well, let's find out. Yeah. Okay, so we want to work out h of negative x, which is 2 times negative x. Okay, so let's call this negative 2x. Let's factor the negative out of there, right, out of here, so that we get an x minus 3 here. Now, the negatives cancel top and bottom. We get 2x over x minus 3. So this is 2x, x plus 3. Are they the same? Is it the negative of? No, so it's neither. Okay, neither. There is no symmetry. Okay, decision time. Do we do the last one or leave it till tomorrow? Yeah, do the last one? Okay. I think we can do this. We can do this. This is vertical asymptotes, right? It's back to limits. It's like easy stuff. Okay? Graphs of three functions are shown. Use the graphs to state the value of each of the following limits. Okay, so f of x is equal to 1 over x squared. And we have, where'd they go? Oh. They got big, and they moved to a separate sheet. You just have them lined up, right? Okay, but you're looking at something that looks like this. So the limit as x approaches 0 from below of f of x is infinity, right? Positive infinity, so we don't put a sign on it, right? We just write infinity. It's late. Yeah, I know the first one was better. Maybe I'll just try and do it sideways, eh?
It's because you're using red markers.
It's gotten worse.
Just circles.
I think that's worse. The limit as x approaches 0 from above is? That's better. And so therefore, since the two one-sided limits are the same, then the limit is? And remember when we first did this, the book would say does not exist, right? But that's why we started saying back then, yeah, really it's positive infinity, right? Okay? The limit as x approaches -4 from below is? And as it approaches from above, it is. And therefore, it exists, and it is. Well, okay, it doesn't exist, but it is. Okay, negative infinity. As opposed to the next one where it won't exist because it doesn't, because they're different, right? The limit as h approaches, or sorry, as x approaches -2 from below is positive infinity. As it approaches -2 from above, negative infinity. And so as it approaches -2, does not exist. 3 from below. 3 from above. And so does not exist, right? Okay. All three functions are discontinuous. Because the above limits are infinity and negative infinity, this type of discontinuity is called an infinite discontinuity, and the limit is called an infinite limit. And if any one of these is true, then there's a vertical asymptote at x equals a. So if you approach a from below and get infinity or negative infinity, if you approach a from above and get infinity or negative infinity, there's an asymptote there, right? And whether they both go up or there's still an asymptote. If you're given the equation of a function but not its graph, how would you determine if there were any vertical asymptotes? Yeah, so you're looking for what value in the denominator is going to give me a 0 because I can't use that value, and therefore there will be a vertical asymptote. So if a function has a vertical asymptote at x equals a, then a is a non-permissible value. Where do we get those from? They're the values of x which make the denominator 0, right? So we factor it and we look for it. Note, the converse is not necessarily true. Do you guys ever do, you didn't do reasoning, did you? You'd converse and contrapositive and all that? You guys, no. It used to be in the old 20 course. It doesn't matter. Not every non-permissible value produces a vertical asymptote. So just because there's a non-permissible value, it doesn't mean there's a vertical asymptote. Okay? What else could there be? Could be like a point discontinuity, right? So, you know, if somebody doesn't know, you could say you don't know your asymptote from a hole in the graph. Anyway. I like that one. Anyway, for example, show that x squared minus 9 over x minus 2x minus 15 has two non-permissible values, but only one vertical asymptote. So you factor it, right? Okay, so what do we got? Well, you have two non-permissible values, right? It can't be -3, it can't be +5. But these two graphs are the same, right? This graph and this graph are the same. Only this graph has the asymptote, right? Because you can't have 5. Okay? This graph here, this, you can put in a 3. Well, you can't put in, or sorry, -3. Well, you can't really, but what's there? That's a point discontinuity. Okay? So we have an asymptote when x equals 5 and a point discontinuity in -3. Okay? So just because there's a non-permissive value, it doesn't mean there's an asymptote there, right? You need to go a little further. Determine each of the following limits. Okay, so what do we got? Like 1, 2, 5, 6 things to do, and then we're done. The limit as x approaches 6 from below. So just think 5.99999. So we got 5 over some really close number to 6, but lower than it, -6. That makes this a small negative value, right? So this is equal to 5 over a small negative number, which will be -infinity. Okay, well, A was easy, B is kind of just easy. So now you're approaching 6 from above. So you got like 6.1, right, which will give you +0.1. We get 6.0000001. It's still going to be a positive. So this will be equal to 5 over a small positive, which will be positive infinity, right, or just infinity. Okay, so we're just above 6, right? So I just think, you know, if you think 6.1 and sort of 6.01, just say it's positive, right? This will be positive. This is below 6, this is going to be negative. C, where are we going here? We've got -1 from below. So if it's -1, then the x is going to be a negative, right? So we're -1 from below negative, like -1.1 kind of thing, right? Okay, so what do we got here? We have, well, okay, wait, let's do this. Okay, so we can look at this. So this will be negative, right? The x up top is negative. You're approaching -1 from below, so you're bigger than, you know, you're -1.1 or whatever. So this will be negative. And this is a negative, well, sorry, this will be a small negative. And this one will just be a negative, right? So, because these guys are really going to be the same number almost. Really close anyway. And so we get -infinity. Okay, so negative over negative, that's positive. We got a small negative left here, right? So we have 3 negatives, that makes a negative. And then if we do the same deal, -1 from above. Okay, so again, we're going to do this. So it's -1, it's negative, so x is still a negative number, so this is negative. -1 from above is like -0.9, so you know this is going to be a small positive number. And you're subtracting -1 from something, that's going to be a negative number. So the negative and the negative make a positive, and the small positive means you're going to positive infinity. Okay, 2 more. They're a little bigger, but
Why is this in this unit?
What is this? Vertical asymptotes?
Like the limit.
It's well, it's kind of back to limits. It's all about curve sketching. So what we got to do is we got to put together a whole bunch of information that we know about the curve, right? So we've got the first derivative, which gives us the intervals of increase and decrease, right? We need to know if there's a vertical asymptote and which way it goes, right? Are we going like this and this? Are they both doing this? So when we go to sketch it, we're going to say, okay, look, I know there's an asymptote here. Okay, the first derivative, I know I'm increasing on this interval. I know I'm decreasing on this interval or whatever, right? So that I gotta have a positive slope or negative slope. We put all of that together, and it's about 6 or 8 different things that we do for each graph, right? We look at this, we look at this, we look at this. We put that all together, we can sketch the graph. Okay? Yeah, or you could just get a computer and say, sketch me the graph. But the thing is, we can get the information that computers can't always show you, right? Because the information comes out, we say, you know, because you could be doing some weird stuff in these graphs, right? They can start sort of oscillating and stuff like that. The calculus will give us those answers and numbers that if you don't look closely or properly at the graph that a machine gives you, you'll miss, right? Because you just won't see that something's happening in this really little tiny interval here, but the calculus will say, hey, there's something happening in this really tiny interval here, which might be the difference between the bridge staying up and falling down. Okay, which is why we don't just rely on, you know. You ever see that Calvin and Hobbes cartoon? It's like Calvin with his dad. It says, bridge, you know, limit, weight limit, you know, 10 tons or whatever. He says, Dad, how do they do that? He says, oh, they just keep driving heavier and heavier trucks over it until it collapses, and then they rebuild it and they put the sign up. Okay, we know, don't go over this weight limit. Okay, for each function, determine the vertical asymptotes and sketch the graph near these asymptotes, right? So when are we going to have a problem here? We're going to have a problem when x is equal to 1, right? That's where the asymptote is. So then we want to say, okay, so what's happening as we approach 1 from below? What's happening as we approach 1 from above? And then we can draw a sketch of the asymptote, right? And it's either, right, it's either they're both up, they're both down, they're this way, or they're that way, right? Like one's up and one's down, but I don't know which one, right? And we need to know that, right? In order to sketch a curve properly, you need to know. Are they both up? Are they both down? Is the left up and the right down, or vice versa? So this is all part of curve sketching. Okay, so let's do the limit as x approaches 1 from below of 3 minus 2 over x minus 1 squared. Okay, so that's going to be equal to 3 minus 2. Okay, if you're approaching 1 from below, then this is going to be a negative number, but it's going to get squared, so it's just going to be a small positive number, right? So small positive. Okay, and so you've got 3 minus, now 2 over a small positive is infinity, but you're going 3 minus infinity, you've got negative infinity. And you can say, okay, the same thing's going to happen when you approach 1 from above, because this is still going to be a small positive, right? It doesn't matter, you know, it's still going to be a small positive, and so it's really the same, right? But let's do it. So the limit as x approaches 1 from above of 3 minus 2 over x minus 1 squared is 3 minus 2 over a small positive, which is also negative infinity. Then we'll extend the page and we'll sketch that. So that's 1, and we've got, okay. So that's what you're going to do in curve sketching, right? When you sketch this curve, you're going to say, I have an asymptote at 1. This is the behavior around that asymptote, right? And then you also do your intervals of increase and decrease and other stuff yet to be learned, but can wait till after the break. Okay, last one. So this is x times x plus 4 over, what, x plus 5, no. Yeah, I wanted to get it wrong, just so somebody would say, no, that's wrong, and I'd say, thank God you're checking, you're foiling. Okay, because really, that's a bad place. It's not losing the half a mark or the mark for doing that wrong, right? It's the grief that it causes afterwards. That's the problem, right? It's like, then, you know, you're off the main highway. You're on gravel roads. And you don't know how you got there, and the GPS is leading you to a lake. And, you know, you're just going to follow it there. Okay, so x squared minus 2 plus 5 is plus 3 minus 2. Right? Because you get these asymptotes wrong, and what happens? Well, the whole graph is off, right? And then things really shouldn't make sense. At some point, you should be looking and saying, that makes no sense. Hopefully. However, you wasted 20 minutes getting there, so, you know. Okay, anyways, there's nothing that cancels, right? So there's no hole in the graph. But there's two asymptotes, at -5 and at +2. So we need to examine x equals -5. We need to do it from the left. We need to do it from the right. We need to do x equals 2. We need to do it from the left. We need to do it from the right. We need to do it in under 10 minutes, but we can do this. Okay, so the limit as x approaches -5, from below of x times x plus 4 over x plus 5 times x minus 2. Okay, so if you approach -5 from below of x, that's negative. When you add 4 to something that's around -5, that's also negative. When you're approaching -5 from below, you're a bigger negative. And when you add 5 to that, you're still going to be negative, but you'll be a small negative. And when you subtract 2 from a negative number then you're going to get a negative. Okay, so how many negatives do we have? So what does that become? Positive. So it's positive infinity. Okay, as we approach -5 from above, of x, okay, so it's still -5, so the x is negative. You're still adding 4 to something that's around -5, so that's still negative. If you're approaching -5 from above, and then you're adding 5 to that, you're going to get a small positive, right? So small positive. And when you subtract 2 from an already negative number, that's just going to be negative. So what's the sign on this? Negative, right? 3 negatives. Okay, so now we know what's happening at -5, right? Now we got to figure out what's happening at 2. So the limit as x approaches 2 from below, x times x plus 4 over x plus 5. Okay, so you can kind of look at this and say, hey, that's positive, that's positive, that's positive, right? Because that's just 2, that's going to be like around a 6, that's going to be around a 7. It's really only this guy that matters here, right? Because they're all positive. So that's equal to, okay, so I got a positive, and I got a positive, and I got a positive, and I'm approaching 2 from below, and I'm subtracting 2, so that's going to be a small negative, right? So a small negative, which makes this whole thing negative infinity, right? Okay, and then the limit as x approaches 2 from above. Hey, look at this. We're going to do it. See, all you need to do calculus is a whole pile of paper, a pencil, and a really good eraser. Okay, so again, right, this is positive, this is positive, this is positive, right? So we got a positive, we got a positive, we got a positive, and we've got 2 from above, and you're subtracting 2. Going to be positive, but small. Small positive. which will be positive infinity, right? They're all positive. Okay, and now we can sketch this. What? Okay, so what do we have? -5, +2, and we had what? -5 from below was positive infinity. -5 from above was negative infinity. -2 from below was negative infinity. -2 from above was positive infinity. Okay? So that's all big part of curve sketching, right? So we're just getting the skills leading up to curve sketching, which is I need to figure out where the asymptotes are, where the holes are, the point discontinuities, and what the behavior is around those asymptotes. Look, we set a new record. 1 hour, 20 minutes, and 49 seconds.